Okay, so continuing with our linear systems of differential equations, here's some notation that we want to be familiar with. So if I write the vector x prime equals a times x, by the way, this prime here denotes the derivative with respect to t, so you could write x prime is the same as dx over dt. Okay, so we're thinking of that. Sorry about the squeaky chair. We're thinking of that as the matrix A times x, right? And so writing out what those things are, x prime is x1 prime and x2 prime. That's a parametric set of equations. And then we have our A, B, C, D. That's the matrix A. And then the vector x. And then by our definition of matrix vector multiplication, that's the same thing as our linear system of differential equations. Good. Now, we know that a solution to the DE, right, is a function x that satisfies the differential equation. God, I need to grease up this chair or something. A solution to the differential equation is x of t that satisfies the DE. Okay, and so in particular, you'll remember that an equilibrium solution is a constant solution that satisfies our differential equation, and so in that case, set the derivative is equal to 0, right? And so to find the equilibrium, we would have ax1 plus bx2 equal to 0, and cx1 plus dx2 equal to 0. And so, of course, x1 equals x2 equals 0 is always a solution. So the origin is always an equilibrium solution. So the question is are there other solutions? And the way to tell from Cramer's rule, other solutions exist if the determinant of A, B, C, D equals 0, right? Because that means that the two equations are actually the same line. Good. So let's try a specific equation now. How about show that x of t equals e to the minus t times the vector 1, 2 solves the system x1 prime, x2 prime equals 3 minus 2, 2 minus 2, x1, x2. Good. So how are we going to do that? Well, first off, we need to differentiate. By the way, I've written this here, but x of t could be written as x1 of t, x2 of t, right? And so that would be, in this case, you could write it as e to the minus t and 2e to the minus t. So that when you differentiate, we get minus e to the minus t and minus 2e to the minus t. But notice that you could have written that as minus e to the minus t times 1, 2. And so going from here to here, do you see a shortcut? Yeah, this thing right here is the only thing that had anything to do with t, right? Explicitly. And so you could just differentiate that, right? And just the vector just kind of comes along for the ride. Very good. So that is the derivative. So we've computed this side of our differential equation. Now we need to compute this side of our differential equation. So let's do that. So we have 3 minus 2, 2 minus 2 times our e to the minus t, 2e to the minus t. And let's compute that. So that's going to be 3 times e to the minus t minus 4 times e to the minus t. And then 2e to the minus t minus 4 e to the minus t. And so that's going to be minus e to the minus t minus 2e to the minus t. And of course that is exactly what we wanted. Okay, so the two things are equal to each other. Very good. And so therefore what we have shown is that this function right here, this parametric function, or parametric set of functions, solves this differential equation, right? Very good. All right. Let's see. So what I want to do now is I want to look to see what would have to happen if I were to get a general solution to my system of differential equations. And so I'm going to set this up. I'm going to pause for a second and write down the stuff that I want to start with. Be right back. All right, so I've got my ansatz here. Notice that this is very much like the last example that we had. I'm going to assume that my solution is of the form e to the lambda t times the vector v1, v2. Or if I want to write that in compact form, I could just say e to the lambda t times the vector v. Now, I would like to plug this into my system of differential equations just to see what has to be true about lambda and v in order for x to solve the system. Right, so let's go ahead and plug in our ansatz into the system and see what we get. So on the left-hand side of my system, I've got x prime is going to be equal to lambda e to the lambda t times v1, v2. Right, which you could write again as lambda e to the lambda t times v1, lambda e to the lambda t times v2. Good, so that takes care of the left-hand side of my equation. Now for the right-hand side, I get a, b, c, d times lambda e to the, oops, no lambda there. It's just e to the lambda t times v1 and e to the lambda t times v2. And so just multiplying that out, right, I get a e to the lambda t v1 plus b e to the lambda t v2 and c e to the lambda t v1 plus d e to the lambda t v2. Good. Now for us to solve the differential equation, this upper equation must be equal to the lower, and so therefore we have a big mess. Oh, let me just rewrite it in as a system of equations. That's a e to the lambda t v1 plus b. Don't write this down yet because it's a big mess right now, but it's going to simplify really fast. And then c e to the lambda t v1 plus d e to the lambda t v2 is equal to lambda e to the lambda t v2. Good. Now what you'll notice is e to the lambda t is everywhere, so we can divide both sides of the system by e to the lambda t, and therefore we can rewrite the system as AV1 plus BV2 equals lambda V1, and CV1 plus DV2 is equal to lambda V2. Okay, and now what I can do is I can subtract lambda V1 from both sides and lambda V2 from both sides, and I can rewrite the system of equations as the following. And this is the important system of equations that we want to remember. A minus lambda V1 plus B V2 equals 0, and C V1 plus D minus lambda V2 equals 0. This is the key system of equations that we need to know in order to solve this differential equation. All right? And so, how many solutions are there to this system of equations? Well, we know that V1 equals 0 and V2 equals 0 is always a solution. But we want to be sure, we want the vector V not to be equal to 0 by definition. So the vector V cannot be 0 in our system. And so that means that this only has a solution when? Do you remember Cramer's rule, determinant? Yes, the system has a solution, has a non-zero solution let me write that over here. Solution only if the determinant of a minus lambda b c d minus lambda is equal to 0. Good. In that case, then the system does have a solution, and notice when you plug that solution into the system, that's an infinite number of solutions, right? So that means that these two equations are the same line, and so therefore we can write down the vector v just as we did in the last video. Okay, so let's see here. Maybe we'll pause here. Well, I'll help you in one of the homework problems. Let's go ahead and see what happens when I take this determinant. What do I get? A minus lambda times d minus lambda minus bc equals 0. Now notice if I multiply this out, what do I get? AD minus lambda d minus lambda a minus bc equals 0. Oops, I forgot my lambda squared. And so now, notice that if I rewrite this, I could rewrite it as lambda squared minus a plus d times lambda plus ad minus bc equals 0. So this setting the determinant equal to 0 means you have to solve this equation. By the way, this has a special name attached to it. This is called the characteristic equation. We've heard that name before many times. And in fact, remember we said that a system of equations can be written as a second-order differential equation, and then the second-order differential equation can be solved using Chapter 3. Well, Chapter 3 uses a characteristic equation. The characteristic equation from Chapter 3 and the characteristic equation that you're looking at right here are the same characteristic equations. So it's not an accident that we're calling it the same exact thing. Good. So, yeah, we're running out of time for this video. I think we'll save the continuation for the next day's class. So we'll stop here for today. Take a look at the homework, and we'll be back next Wednesday.